Alrighty. Happy New Year, Merry Christmas, and Happy Holidays. Welcome to another Tech Day. I want to start with this fantastic game. It's basically for me just a warm up before I start doing some other things, some more complex things. Basically, this is called Guess the Angle. The number of the angle is 331. And I need to guess. So, it's not a full circle, but it's almost a full circle. This could be 15 to 20. I don't think it's more than 20 degrees. So if a full circle is 360 minus 20, it should be 340. And if it shows me incorrect guess, most probably it will be incorrect, I will calibrate. Make it 344. It's bigger than 344. 350, 360. So this is not 16. If this is 90, this is 45. This is 22. Might be even 11, around 11 or 12. So if it's 12, it should be 348. And this is how it's done. A calibrated guess. So this angle right here, it's around 45 degrees. So I'm gonna say it's 90 plus 45, maybe not 45. Let's say 90 plus 48, 118. It's bigger than 118. Makes sense. It's not exactly that means angles. It's not exactly wait, where is it? Give me a referential image here. It's not a 45 degree. It's actually opened a lot more than a 45 degree angle. I would even say this could be a 50 degree angle. So 90 plus, let's say 52, it's 122, bigger than 122. One two eight, 127, bigger than 127. What? I have one guess left, and it's definitely bigger than 127, which means that if this is 90, this one is oh, I'm an idiot. For some reason, this is actually only 37 degrees. Oh god. So if this was a 42 degree angle plus 90, it should be 132, right? 136. I'm an idiot. Let's do another one. Angle number 329. This should be simple. It's 30, and it will be less than 30. It's definitely bigger than 26. So I can do 28, and I would guess it in the next one, but I want to do something. It's 28. It is 28. I'm guessing another angle. Angle 328. Let me close this. So I'm guessing angle 328. We have a 90 degree here, and this one, I'm not gonna make the same mistake. I did the last time. So this here, it's less than 30. It's definitely less than 30. This angle, where the red arrow crosses the 90-degree mark. Less than 30 is maybe 22, so it should be 114. I know the 22 plus 90 is 112. I calibrated a little and I guessed it. For some reason, I managed to guess it correctly. Let's do another one. Let's do another one. Enter an even number. I just noticed that it says enter an even number. Is this helping me? Giving me some tips on how to beat it? No idea. But enter an even number. Okay, so let me think about it. This is 180 degrees. Basically, as you lie flat, it's 180 degrees. It's half of a circle. This is a slight bend. If you've ever been to a gym, you know that they have these incline benches. And this is a pretty slight bend. And if you did a bench, most people will say, okay, it's almost a flat one. So it's 180. And I'm not gonna say it's more than 10 here. I'm gonna say 190. I am unbeatable. If there is a competition in which people are guessing angles, I would hit it immediately. Again, it's an even number. Let's do one more. Let's do one more, and then I'm gonna officially start working. Okay, so this angle right here. Okay, so we are closing a circle. It almost reminds me of Pac-Man right here. If you turn it yellow, it will most certainly be extremely similar. And as a matter of fact, if I would Google what angle Pac-Man's mouth is, I would most probably take the same guess. No, first, you know what I'm gonna do? I'm gonna guess it, and then I'm gonna search and Google and find more information about that yellow bastard. First of all, it's 90. This is 90 right here, and so it's 270. It's not more than 20s. If I type in 290, it's definitely gonna be less. I'm gonna type 286. It's bigger than 286. 290. Bigger than 290. So I did a bit of a miscalculation here. If this is, yeah, it's 20 something. So let's do 294, 296, it's 298. Pac-Man. Pac-Man. Oh, so there is this classic game online, but wait. Pac-Man mouth angle. Official. The figure below shows an image of Pac-Man. But why are there so many ads here? Shut up. Of Pac-Man from the classic video game. The mouth of Pac-Man forms a central angle of 55 degrees. No, 55 degrees. So 360 minus 55, it's 305. So it's Not as close as I imagine it would be, but all right. Now, do you remember that I started with the book Structure and Interpretation of Computer Programs? And if you remember that, you know that we finished the first chapter mostly, and we came across the exercises. Usually I love it to do exercises. I think exercises are the best part of a textbook. I would skip maybe 90, maybe not 90, 60 to 70% of all the theoretical mumbo jumbo, and I would jump straight into exercises, and then I would reference the theoretical later on. That's the way I used to do it. So now we will actually do some of that. Let me just go, where's my document? Okay, I have the document right here. I will. Okay, I will set everything up now. So it says here, observe that our model of evaluation allows for combinations whose operators are compound expressions. Use this observation to describe the behavior of the following procedure. I'm going to write this procedure right here. Okay, so this is the procedure. And it says, observe that our model of evaluation allows for combinations whose operators are compound expressions. So we need to learn the behavior of this procedure. Basically, what we need to do is to analyze and see what is being done here. So we need to explain the behavior. So I think the key thing here, I assume this is no, not once. Come on, 160 is the exact width. You must be kidding me. Okay. So what's the key idea here? The idea is, oh yeah, first of all, I assume this is the name, and these are the params, the properties that we are providing in this method. And what I found interesting is this section right here. What I think it happens here is that the operator position can itself be an expression. So if I remove this highlight here, I have this check right here. If b is greater than 0, it's evaluating to either the plus procedure or the minus procedure, and then the resulting procedure is applied to a and b. basically, if b is greater than 0, what are we doing? We are doing plus a b. But if b is less or equal than 0, we would do minus a and b. But there's another thing. So if b less than 0, right? So we are solving this equation right here. But because b is negative, so this is going to be a minus negative b. In the end, it's just going to be a plus b, or a plus the absolute value. That's why the name is a minus plus absolute b. Okay. All right. So let's do another example right here. Keep it down a bit to have a blank space. It says here, Ben Bit Diddle. A name to remember. Hopefully it's a real name. Ben Bit Diddle has invented a test to determine whether the interpreter he is faced with is using applicative order evaluation or normal order evaluation. He defines the following two procedures. So he defines some procedures, then he evaluates the expression. What behavior will Ben observe with an interpreter that uses applicative order evaluation? What behavior will he observe with an interpreter that uses normal order evaluation? Explain your answer. And then it says in the notes, assume that the evaluation rule for the special form if is the same whether the interpreter is using normal or applicative order. The predicate expression is evaluated first, and the result determines whether to evaluate the consequent or the alternative expression. Am I getting filtered by this book in the first chapter? I have no idea what is being said here. But first, okay, let's write. We have been given some procedures. Okay, so we are given this, and we need to evaluate test 0 on B. So let me read again. So we have our friend Ben Bidittle. I'm gonna skip everything related to the setup of the exercise. So two terms, applicative order evaluation or normal order evaluation. So we have these two procedures, then we evaluate the expression. So we have everything here already written. What behavior will we observe with one versus another? Okay, so this is applicative order evaluation or eager evaluation. Applicative order means evaluate the operator. So if we are referencing this right here, if we use applicative order evaluation, It means that we would evaluate the operator test and evaluate all arguments before calling test. Oh, I should ask myself, what happens under applicative order evaluation, applicative or eager evaluation? We evaluate the operator and all arguments before calling test. Okay, so we first try to evaluate the 0 and then the p. What happens with the p here, because phi is another procedure, p is expanding p forever. Like right here, we are defining p, we are calling p, and it expands forever, infinitely. It's an infinite recursion. So the interpreter never returns. It's an infinite loop. It's a stack overflow because it gets stuck evaluating p before it even enters test. So that's what applicative order means. Now, what is a normal order evaluation? So, and now, what happens under normal order evaluation, or lazy or substitute first? It means we don't evaluate arguments until they're needed. So if we do, let me just change the color here, maybe use this. If we evaluate the same procedure, we are actually substituting the test or the body right here. And now we evaluate if. So if 0 equals 0, it's evaluated first. It's true. So then the consequent 0 is evaluated and returned. The alternative b, I don't know why I'm writing so many arrows, it's getting confusing even to me, but the alternative is never evaluated. So here the interpreter is gonna return a value. But with applicative order, we actually diverge. We get into an infinite recursion because we try to evaluate this p. Interesting. Now, let's do another one. Let me skip this. Let's do it on a new page. It says here, Alyssa P hacker doesn't see why if needs to be provided as a special form. Why can't I just define it as an ordinary procedure in terms of cont? She asks. Alyssa's friend Eva Lou Ater, these names are ridiculous, claims this can indeed be done, and she defines a new version of it. And Eva demonstrates the program for Alyssa, and delighted, Alyssa uses the new if to rewrite the square root program. And then it asks, what happens when Alyssa attempts to use this compute the square roots? First of all, wait. Okay. First of all, let's go a bit back. Let's learn. Let's conceptually learn. let's make a distinction between a mathematical function and a computer procedure. A mathematical definition is declarative. It's basically what is true. They define things like this. Let's say we have a square root of x. And we can say the square root of x is y. The y such that y is greater or equal than 0 and y squared is equal to x. This is a perfectly valid math definition. It tells us what square root means, but it doesn't tell us how to compute it. Basically, if we write something like this here, like we can define the procedure and we can do something like this. We can say, okay, let's define. I'm gonna omit some of the parentheses. Please don't take this against me. I don't need this here. So this is defined the square root. It's the y and greater equal y0 equal where y. So what is this saying? Okay, we are defining a procedure named square root squirt, and it's the y and basically saying, okay, return me this. It's saying like return me this y that satisfies the property. But how do we find that y? It's the same as saying, okay, give me the winning lottery ticket number. So we describe the answer, but we have no steps to obtain it. It begs the question, basically. It insists upon itself. So we have these two key distinctions. We have something called declarative knowledge, and we have something called imperative knowledge. So declarative knowledge is describing facts or properties. The why, such as that. And imperative knowledge is describing a method or describing some steps. So what programming needs is more effective procedure. So we need a finite mechanical method. We need a way to reach the end result. So what do we have here? let's see how we can actually calculate a square root. So we have something called a Newton's method, which is a procedure to approximate the square root of x. Okay, Newton's method. It gives us a repeatable rule. It's something that is easily transcribed into a concrete way of finding or approximating the square root of x. Basically, if you have a guess for y, it basically says if you have guess y or square root of x, a better guess is new guess is equal to y plus x over y divided by 2. Basically, if y is too big, x over y will be too small, and averaging them pulls us towards the true root. And we can do an example for, let's say, okay, let's do an example. Let's say the square root of 25. And let's say our initial guess is 3. So we plug here 3, and we have 3 plus 25 over 3 divided by 2. This right here is 11.333 over 2. 11.333 over 2. It's 5.6665. So this value will be 5.6. And then I plug in 5.6665 into the same formula. Okay, now this is a way how we can implement the square root. Now let's write a pattern. We're going to refine it until it's good enough. Let's have a core idea. Let's have a core loop idea. Let's start with a guess. If the guess is good enough, let's return it. Otherwise, let's improve the guess and try again. I'm gonna write it right here. Again, I'm gonna omit a couple of parentheses. Let's see. Square root iteratively. Guess, and we have the value x. And let's have if good enough. What have I done? Yes, x, and let's return yes. Otherwise, Let's improve our guess here. Improve guess x x. If the guess is good enough. Otherwise, let's call this method again with a better guess. Now we need to create the improve method as well, and also the good enough method. Both of these should be defined, both of these procedures. So what should improve look like? Let's use define. Let's just use def. I want to do this. So def improve. We have our guess. We have x. What do we need to do here? We need to find the average of but not the average first, because we first need to do something else. We need to do the x and guess, and this will be x over guess, and then average. Average will do. Average is just another method that does a plus b over 2. It's another method we need to create. Ah, shit. All right. Okay, so I need to define average as well. What am I returning here? Average takes two values, and what I want to do is I want to return. I want to return this format. So how we can do this? First of all, I need plus x, y. And I just need to divide it by 2. And this should be enough. This should definitely be right. Do I have somewhere an online list interpreter? Online list interpreter. Okay, it's gonna give me. I did open this already, but this won't work. Output hello world. What if I do here plus 5 will this work? Program did not output anything. Do I need to output anything? Format D. Let's see. Plus 5. Will this work? It doesn't. Do I need to print this out properly? Format, maybe I don't need the T here. Okay, so how to print out values in Lisp. Print format. The print hello. For printing list. Print, why is this uppercase? Print 5. Alright, so this works. It took me some time. Don't. Don't leave me just yet. It takes a bit of time for this to enter my mind, to enter my consciousness, to stick. All right, so we have all of these ideas, and we want to turn all of these ideas into code. Okay, let me also do this. Good enough is basically just the threshold method. How would a good enough method look like? So it's good enough, and let me just Google it here. No, let's use here. Let's use Brave. The search engine isn't the best, but it gets the job done. So what I need to do here, I need to Newton's method threshold. Threshold. I think it will show it here. Stopping criteria. Yes. I have no idea what this means. What is the stopping criteria? I need a better stopping criteria. Wait, let me just find what's the simple stopping criteria. Let me open the Wikipedia article. All right, so where is the threshold here? Where is the threshold? How do we find? Where's my tablet? Let me try to guess. So good enough. If I have here my guess and my x. So I need to square the guess first of all. I think I already have the square method, so square guess. And now I'm comparing it to x. So minus x, I'm gonna take the absolute value. And if the difference is small, under 0.0001, let's stop. We're saying stop when guess is close enough to x. So this is a tolerance-based approximation. It's not an exact answer. That's how most real numeric computing works. Okay. The thing is now, we haven't learned loops, but this is an iterative approach because it's foundational. Even if our language has no for or while, you can still loop by writing a function that calls itself, and that's called recursion. Here in the squared iter method, this method is calling itself. It has the loop shape, it has one changing state, it has one constant input, and it's repeating until condition is satisfied. Okay. Let me stop here. And let's see if there's anything new in hacker news. Confirm you're a human being. I'm not a robot. I'm definitely not one. What do we have? Lessons from 14 years at Google. Adios money. Oh, I know this guy. Why is he famous? What did he build? Beyond wipe coding. You know what? This is also something that I would want to find somewhere to buy. Let me just... Beyond wipe coding, that's the name of the book. Beyond wipe coding. Have I read something of his stoic mind? Backbone JS applicative. In one of my older videos, I actually was researching about Backbone, so it's really interesting. JavaScript design pattern. But this is not it. I director at Google Cloud AI, focus on helping developers. Chrome, he worked on that. He did write something, either an article that I read or a book that I read, and I was really impressed. Ooh, an interactive guide on how browsers works. The unbearable joy of sitting alone in a cafe. Yeah. Huh. Ooh, neural networks. Web development is fun again. A lot of these are pretty good. Okay. Let's start with Adios money. 21 lessons from 14 years at Google. When I joined Google 14 years ago, I thought the job was about writing great code. I was partly right, but the longer I stayed, the more I realized that engineers who thrive aren't necessarily the best programmers. They're the ones who have figured out how to navigate everything around the code, the people, the politics, the alignment, the ambiguity. Which is basically true. I worked in a couple of companies, and there's a lot of petty politics. There's a lot of petty people. There's a lot of gossiping, talking behind someone's back, and it's anti-productive in a sense, but it's also something that is inherently human. I did, you know, I knew that, for example, if you are working in a market or on a construction, or if you're a sports person, like an athlete or a footballer, I knew that, you know, you will have these games, these petty games here, but I didn't expect the same thing in a tech company. And then when I came and I saw how it works and how it is, I was like, oh, all right. These lessons are what I wish I would know earlier. Some would have saved me months of frustration, others took years to fully understand. None of them are about any specific technologies. They're about the patterns that keep showing up, project after project, team after team. I'm sharing them because I've benefited enormously from engineers who did the same for me. Consider this my attempt to pay it forward. All right, Adi, let's see what lessons and gifts you are giving us. And also, I'm really interested in whether this was AI generated. Hopefully not. The best engineers are obsessed with solving user problems. Makes sense. Basically, based on the title, I think I know what is behind this. Yeah, don't focus on a technology. We all have done it. But the best engineers, they create the most value work backwards. They become obsessed with understanding user problems deeply and let the solutions emerge from that understanding. User obsession means spending time in support tickets, talking to users, watching users struggle, asking why until you hit bedrock. The engineer who truly understands the problem often finds that the elegant solution is simpler than anyone expected. Okay, being right is cheap. Getting to right together is the real work. Makes sense. There is a lot of technical arguments in any workplace. People generate resentment by being the smartest person in the room. And the cost shows up later as mysterious execution issues and strange resistance. So you shouldn't focus on being right. It's entering discussions on fixing the problem, creating space for others. Yada, yada, yada. All right. Bias towards action. Ship. You can edit a bad page, but you can't edit a blank one. Makes sense. Makes sense. The quest for perfection is paralyzing. I watched engineers spend weeks debating the ideal architecture for something they've never built. The perfect solution rarely emerges from thought alone, it emerges from contact with reality. AI can in many ways help here. Makes sense. Okay. This is definitely either partially or fully AI written. Clarity, seniority, cleverness is overhead. Clarity, seniority, cleverness is overhead. Okay, I don't understand. The instinct to write clever code is almost universal among engineers. So it's as you write more clever code, you are more you are more competent, you are better. But we need to focus on clarity. We need to optimize our code for strangers that will work and maintain our code. The senior engineers I respect most have learned to trade cleverness for clarity every time. Novelty is a loan you repay in outages, hiring, and cognitive overhead. Makes sense. Makes sense. Okay, we have technology choices. And we should consider them something as innovation token budgets. So it's not never innovate. It's innovate only when where you're uniquely paid to innovate. Everything else should be default to boring because boring has no failure modes. All right. Your code doesn't advocate for you. People do. Makes sense. Makes sense. Code static. The people who read your code, the people who work later on your code are the ones who are recommending you or advising for you. Yeah, you need to make the value chain legible to everyone, including yourself. The best code is the code you never had to write. Makes sense. We celebrate creation in engineering culture. Nobody gets promoted for deleting code, even though deletion often improves a system more than addition. Addition. Yeah, his name is Addy. Every line of code you don't write is a line you never have to debug, maintain, or explain before you build. Exhaust the question, what would happen if we just didn't? Sometimes the answer is nothing bad, and that's your solution. You know what the issue with these lessons and gifts is? That you only can apply them retroactively after you build something. There is no way that you are crunching time. You need a deadline to finish, and suddenly you are sitting there thinking, oh, how can I improve this? How can I make it leaner, better, more readable for the people, for me? This only happens after you done your work and you sit down and you do a summary of your work and you find all the positives and the negatives and you think about the ways of doing things better. At scale, even your bugs have users. With enough users, every observable behavior becomes a dependency, regardless of what you promise. Someone is scraping your API, automating your quirks, caching your bugs. This creates a career level insight. You can't treat compatibility work as maintenance and new features as real work. Compatibility is product. Design your deprecations as migrations with time, tooling, and empathy. Most API design is actually API retirement. Okay. So we have slow teams, and they are actually misaligned teams. I can reference, and I can relate to this as well. I've been on a couple of slow teams, and mostly the issue was communication based. When a project drags, the instinct to blame execution. People aren't working hard enough. The technology is wrong. There are not enough engineers. Usually none of that is the real problem. In large companies, teams are your unit of concurrency, but coordination costs grow geometrically as teams multiply. Most slowness is actual alignment failure, which makes sense. Like, imagine you have a huge project. You have a project that multiple people from in a multinational company are working on. Let's say you have 10 teams of 5 people. These people need to be properly aligned. These people need to work synchronously, like clockwork, in order to provide and build the best product. Otherwise, yeah, things won't work as they should. Focus on what you can control, ignore what you can't. This is actually a pretty good advice generally in life. You can control whether a reorganization happens. You can control the quality of your work. Makes sense. Abstractions don't remove complexity. They move it to the day you are on call. Yeah. This is actually pretty interesting. Every abstraction is a bet that you won't need to understand what's underneath. Sometimes you win that bet, but something always leaks, and when it does, you need to know what you're standing on. Senior engineers keep learning lower level things even as stacks get higher, not out of nostalgia, but out of respect for the moment where the abstraction fails and you're alone with the system at 3 a.m. All right. So for some reason, my man Eddie is repeating that he was working a lot in those early morning hours. Where is he? Lessons from 14 years at Google. Writing forces clarity. The fastest way to learn something better is to try teaching it. Also a pretty good advice. Writing forces clarity. So when I explain a concept to others in a document, a talk, a code review, comment, even just chatting with AI, I discover the gaps in my own understanding. The act of making something legible to someone else makes it more legible to me. Yeah. The work that makes other work possible is priceless and invisible. Okay. It took me a moment to understand. Documentation, onboarding, pair programming, cross-team coordinations. Yeah, it's priceless, but it also can burn you out. Priceless and invisible is a dangerous combination for a career. If you win every debate, you are probably accumulating silent resistance. Okay, so this is most probably related to the first point. When a measure becomes a target, it stops measuring. Every metric you expose to management will eventually be gained, not through malice, but because humans optimize for what's measured. If you track lines of code, you get more lines. If you track velocity, you get inflated estimates. The senior move, respond to every metric request with a pair. One for speed and one for quality or risk. Okay, so how many do we have? Your network outlasts every job you'll ever have. Early in my career, I focused on the work and neglected networking. In hindsight, this was a mistake. Colleagues who invested in relationships inside and outside the company reaped benefits for decades. Yeah, this is actually a pretty good advice. I'm not the kind of person. I'm not networking pretty. They heard about opportunities first, could build bridges faster and get recommended for roles, and co-founded ventures with people. They'll they build trust over the years. Most performance wins come from removing work, not adding cleverness. I think it's also a reference to a past point. Processes exist to reduce uncertainty, not to create paper trails. Eventually, time becomes worth and money. Act accordingly. You trade time for money, and that's fine early in your career. But at some point, the calculus inverts. You start to realize that time is the non-renewable resource. All right, so this whole point isn't about don't work hard, because it says here, I watched senior engineers burn out chasing the next promotion, optimizing for a more percentage points of compensations. So it's mostly like know your worth, know what you want to work on, and time, you can get your time back. So instead of squeezing out these couple percentages, maybe do something more important with the time you have. There are no shortcuts, but there is compounding. Expertise comes from deliberate practice. For years, there is no condensed version, but here's the hopeful part. Learning compounds when it creates new options, not just new trivia. Right, not for engagement, but for clarity. Build reusable primitives, blah, 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 blah. Okay, let me see if there are any interesting comments here. At scale, even your bugs have users. Ha! Okay, okay. So there's first place I worked out of college had a big training seminar for new hires. We heard a story about how they improved load times from around 5 minutes to 30 seconds in the 90s. The feedback was overwhelmingly negative because it destroyed their company culture. Instead of everyone coming into the office, turning on their computers and spending the next 10 minutes chatting and drinking coffee, the software was ready before they even stood up from their desk. So what's the message here? The software you're building doesn't exist in a PRD or a test suite. It's a system that people will interact with out there in the world. Habits will form, workarounds will be developed, bugs will be leaned for actual use cases. And this makes it critically important that you, the software engineer, understands the purpose and real-world usage of your software. In the end, user is the king. "15 years in leadership, worked at 3 jobs, led major transformation at retail, 100 billion of revenue goes, and he ran 55 to 100 million a yearly budget, over 300 FTEs and 3x contractors under my budget. Blah 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 blah. Besides your capabilities and ability that had to be there to get you these positions. Once in these positions, only that matter is politics and ass kissing." Yeah. I know so many people smarter than me always stay lower because they didn't know how to play politics. Only reason I never got higher was I didn't know how to play politics and kiss ass anymore or better. Alright. Good advice. Alright. I need to hit. I need to go. I need to hit the exit button. Thank you so much for watching this and see you in the next one. Bye bye.